Hello everyone, welcome to our lecture 7 on Mechanics and Materials 1. Today we talk about stress. We will have 2 lectures on stress and this is the first lecture on the 2-lecture series on stress. Also we cover sections 1.1 to 1.5 of the Hibbeler book, the first chapter of Hibbeler book obviously. And in particular we talk about the 9th edition of the book. So before I start talking about stress, let's see what we have learned so far. So far we have talked about equilibrium and we have talked about equilibrium of points, rigid bodies, and structures made of rigid bodies, such as truss structures. Now we want to talk about equilibrium of deformable bodies. And basically that's why we need to talk about stresses, because usually when you want to talk about deformable bodies, we are interested to talk about the state of the material inside the material. So we want to know what is happening inside the material, and stress is a quantity that gives us information about the internal material state basically. So in principle, what we want to do is to distinguish between external loading and internal loading. External loading are the usual loads that you apply on the structure, and then you know, for instance, these are the forces that you may apply on the structure. This could be weight, this could be the reactions from the support, and usually you will write governing equations, the balance equations, equations for the forces and the balance of moments to compute the external forces. And that's what we have done so far. But from now on, we also need to talk about internal loading. Now, internal loading connects to stresses, and they are basically appearing in resultant internal loadings. We will make this more clear through this lecture. So, in summary, we have talked about external forces so far. We want to talk about the stresses, but before we can talk about the stresses, we need to better understand what are the internal loadings. Because the internal loadings and the stresses, they go hand in hand, and the connection between them should be clear. Okay, so with that, I would like to talk about internal loadings. For instance, think about a body as shown in the picture. Imagine this is essentially a three-dimensional object like this, and now on that object you have the external forces. For simplicity, imagine that you have only 4 external forces applied on the body: F1, F2, F3, and F4. What I want to do next is to cut this body to basically make a cross section through the body, say through its center, as shown in the picture. And I want to ask myself, or I want to show what happens on that cross section. If you do that, and if you cut the body, you can imagine that you will see that there are a lot of interactions between the points basically from the upper part of the body and the points on the lower part of the body. And these interaction forces on that surface, they look like this. So you would have these very tiny forces acting on different points on that body. And usually this is like a continuum mechanics, so it's a continuous material. I have only drawn a few of them, but you can imagine these are basically infinitely many. Okay, but then if you remember, we have learned that if you have a lot of forces or several forces acting on a body, you can always replace that by a single force and a couple. So you can replace it with a force couple system, and that's what we want to do. So basically, you can say instead of all these, I will be only talking about this resultant internal force, and then this resultant internal moment. Okay, so this is the resultant internal moment, and this is the resultant internal force. Now pay attention, these are internal forces, and basically they will be in equilibrium with external forces that are remaining on that part of the body. Also, again, remember that the resultant forces and moments, these are only useful definitions for calculations. Otherwise, you can imagine that in reality, it's always a distributed force state like this, but that's usually very complicated to handle in calculations. So basically, we replace them by resultant forces and moments. Also remember, if I just cut the upper half of the body instead of the lower half, then I would see a picture like this. So basically what happens between the upper half and the lower half is this action reaction kind of scenario. So basically whatever force you have on the lower half as a resultant force, this is caused by all those little forces whose interactions or whose reactions on the upper body would also exist. Okay, so basically whatever you get for your resultant force, you also get a reaction for the resultant force. So this is kind of interesting because just if you look at this picture, usually for external forces, you just talk about one single force and it has a direction, it has a magnitude. But for internal forces, if you look at this, you should immediately ask yourself, are we talking about the resultant force on the lower surface or on the upper surface? Okay, so internal loadings, they always appear in this combined action reaction or as pairs, as opposed to external forces that are always single forces. Okay, so let's talk about that a little more. If we just focus on that, let's say on that cut out of the body, and then assume that you have the internal resultant force and internal resultant moment, you can imagine that similar to what we have done before, you can also project these forces and moments. Now, two types of the projections are of particular interest for us. One is the tangential projection, whether for the force or the moment. So here I'm talking about the moment on the left, and on the right I'm talking about the force. So if you think about the resultant force Fr and you look at the tangential projection of that onto the plane itself, this will cause a shear. Okay, so you can imagine this would be a usual force that wants to cut the material like with a scissor or something. Okay, so this has this shear type effect. Whereas if you think about the normal component of that, the normal component of that is our usual normal force. It wants to cause an extension or a tension basically in the material. Okay, so these two components, whether it's a normal resultant force or tangential resultant force, they do two very different things, and for that matter we will distinguish between them. We will distinguish between normal forces and shear forces. The same story happens also for the moment. So if you think about the resultant moment and you think about this surface again, the tangential component of that moment is very different from the normal component of that. So the normal component of the moment, if you look at it, it would be something like this. So it wants to twist the member. So if you think about it, if you think this is like a bar or something, and then you have a moment which is normal to that, it wants to basically twist the moment. Okay, and we call this torsional moment. Also, we call it torque. Okay, so, and you can imagine it wants to result in twist. Whereas if you think about the tangential component of that, the tangential component of the moment wants to cause a bending. Okay, so in this example is slightly difficult to show, but imagine if you have a bar now, maybe like this with a rectangular section. If you have a moment like that and it wants to cause a bending. If you think about a moment like this moment is essentially a moment which is tangential with respect to this direction. Okay, with respect to this direction. Okay, so essentially you talk about torsional moment, which is the normal components of the moment, and you talk about bending moment, which is the tangential component of the resultant moment. So again, we have basically four components to be looking at, and for that matter, we always decompose these separately. So if you think about the same body, the same cutout here, you can see what I have done. So instead of the resultant force Fr, we always talk about the resultant shear force and the resultant normal force. And we know the sum of these, so all of them together, or both of them together, it would eventually be exactly as Fr. But Fr alone, it has this mixed nature. We would like to decompose it to a shear force and a normal force, and that's what we do here. The same thing for the moment. Instead of just drawing a resultant moment, I would replace it with these two components, and then I know the t component, or the let's say the normal component, we call it t. It causes a torsion, so t stands for the torsion, or let's say torque, if you want to remember that. And then the tangential component of that wants to cause a bending. Okay, and then again, in this picture, maybe it's difficult to imagine the bending, but if this was a long member like this, you can imagine that it could bend. Okay, due to that moment. All right, so in summary, when we want to talk about internal state of the material or internal resultant forces and moments, there are four quantities of interest that we would like to talk about. One is the normal force N, the next is the shear force V, and these two are essentially the components of the resultant force, internal resultant force. Then we have torque or torsional moment and bending moment M, and these two are the components of the internal resultant moment. So to better understand that, we have some additional explanation here. The normal force N is perpendicular to the cross-sectional area and is developed to resist against pull and push due to external forces. So for instance, you can think of a simple spring under extension by external forces. If you cut the spring in the middle, then the internal force state inside the spring would be a normal force, and that's orthogonal to the cross-sectional area of the spring. If you think about the shear force, on the other hand, the shear force lies on area, and you can imagine that the shear force is orthogonal to the normal force, and their dot product is therefore zero. The shear force is developed when external loads tends to slide two segments of materials over one another. Okay, so you can again imagine a deck of cards, and basically usually we talk about a typical example that if you have a deck of cards stacked on top of one another, when you deform them like this, then basically the forces that you need to do this type of deformation is the shear force, because you want to slide segments of materials over other segments essentially. And then again, if you think about the scissor and how scissor cuts a material, is usually through this type of shear forces. Then we talk about torsional moment or torque, and that's a perpendicular component of the moment, of the resultant moment, and this is developed to resist against twist due to external forces. So if you have a bar and you try to twist that, the internal resultant moment in the bar would be a torque or a torsional moment. Then we have bending moment, and bending moment is the tangential component of the resultant moment and is developed when external forces or external moments tend to bend the body about an axis lying within the plane of area. And then again, a typical example of that would be if you think of a beam or something that you try to bend it. Now, if you cut that, the moment state, the state of the internal moment inside the material would be bending moment. We will have a lot of examples throughout the semester and we will better understand this. And also in today's lecture, we will have two particular exercises. We will come to that. But before coming to the exercises, let's see what happens if we think about a two-dimensional problem. Obviously, for a two-dimensional problem, it's exactly the same story. It's kind of easier to think about a two-dimensional problem. So if you think the coordinate systems are x and y, and then you have this cross-sectional area and you cut the body through that cross-sectional area, you can again think of these different types of reactions that we talked about, except that in this case, you would only get the bending component of the moment, or the tangential component of the moment if you want to. Okay, the torsional component would be out of plane. So in a two-dimensional problem, we cannot exactly show it or work with it. So for a two-dimensional problem, you talk about normal force, shear force, and bending moment. And then again, remember, for a two-dimensional problem, you usually have also three equations for equilibrium. And if you think about those three equations of equilibrium, you can write it as the balance of forces in the x direction, in the y direction, and balance of moments. Now, balance of forces in the x direction, and if you assume this is your coordinate system, the balance of forces in the x direction would give you the normal force N. Balance of forces in the y direction gives you the shear force V. And balance of moments with respect to any point would give you the bending moment M. And again, remember, these are internal. Okay, so we had forces and moments before, but these are internal forces. Okay, so you would write this balance of forces that you are talking about here. It's the balance of internal forces versus external forces. So this is the balance of forces or moments on a section of the body. And if you look at that section On the left part of it, you have external forces. On the right part of it, you have internal forces and moments. Okay, so now these balance equations, again, these are the same equations in principle, but they have this interesting feature that include both internal and external reactions inside them, or forces. Okay, so what we want to do and the procedure for analysis for the examples that come are essentially similar to what we did for method of sections. So when you want to calculate the internal forces and moments, whether it's a 2D problem or a 3D problem, you need to cut the material at a cross section of interest. Okay, so once you cut the material at that cross section of interest, which looks very similar to what we did in method of sections, then you divide the structure based on the segments that you get. So if it is one cut, then you get, let's say, left and right segments. And then you draw the free body diagram on that. Remember, for the free body diagram, you should include support reactions and weights, but also you should remember to include internal forces. So these would be external ones together with weights and other external forces, and then you should always have internal loads, and then you impose equilibrium. And as I said, now the equilibrium equations, they have this interesting mixed feature that they include both internal forces or internal loads and external loads. We have two examples that come now, and we will learn these through exercises together. Our first exercise today is similar to problem 1.1 on page 11 of the Hibbeler book, the 9th edition of the book. Given is the beam clamped on the left hand side, so you have a fixed support here and it can apply forces in x and y direction as well as a moment. On top of the beam, you have a distributed load as shown in the figure. It starts from 0 and it comes all the way to 270 Newton per meter. You are asked to determine the resultant internal loadings acting on the cross section at C. So basically the question is, if we cut the structure here, what are the resultant loadings? And remember, again, it's a two-dimensional example, so the resultant loadings would be N, V, as well as M. So moment, shear force, normal force. Before we start jumping on the solution of the problem, we need to have a very important definition, and this definition is appearing in all the problems that are similar to this throughout the semester, and we will have a lot of those. So it's very important that you very well understand what I mean by this definition and this convention. We have done a very similar thing when we talked about truss structure. So remember, we talked about the forces and force directions. So if you talk about external forces and external moments, usually you define their directions based on the coordinate system that you define. Whereas if you talk about internal forces and internal moments, talking about just the coordinate system is not enough. Because for instance, you can think about a little cut out of the member like this. So let's say we cut a little piece here. So if you cut a little piece of the material, then in order to have that under tension, you need to have forces in opposite directions anyway. If you want it to be under compression, you should also have forces that are opposite to each other. So you cannot exactly talk about the direction of the forces, because then on the left and the right, they have different directions. So for that matter, we decided to define something better than just direction, like better than usual direction that we had based on coordinate system. So we said if the member is under tension, we call that positive. So the forces that result in tension, they are plus forces, they are positive forces. The forces that result in compression, they are minus, they are negative forces. So based on this definition, this would be the graphical representation of the convention that we used for the internal loadings, but only for normal force. So for the normal force, that's how we define our plus convention. And this is exactly in accordance with what we did for truss members. Now we do the same thing for bending. So for bending, we also need to define a convention, and then we assume that if you have a bending moment, so if the member wants to bend like this, so you can imagine if you pour water, it holds the water. So if you have a bending like that, that would be our plus convention for bending moment. And then again, you can imagine on the left and on the right, you would need opposite moments to make that happen, because this thing should be in equilibrium. Okay, so you cannot say for the whole member, you cannot just say what is the direction. On the right hand side, the direction is counterclockwise. On the left hand side, the direction is clockwise. Okay, so this combination of directions would cause a plus convention for moments. So that's what we call positive moment, positive internal moment. Again, it's important that we are talking about internal moments. And that's where the whole complexity is coming from. So then we need to also define something for the shear forces. So if on the left hand side the shear force is upwards, on the right hand side is downwards. So maybe you want to imagine that it tries to turn the piece clockwise. That would be our plus convention for the shear force. So if I tell you shear force is just 5, it doesn't mean that it's 5 upwards or 5 downwards. It means it is 5 downwards on the right part and 5 upwards on the left part. Okay. So this convention is extremely important for what we do from now on, and we hold to this for the rest of the problems, for the rest of the lectures in this series. So in summary, if I want to combine all the three of them in one picture, this would be the picture you are looking at. So again, if you talk about normal forces, plus direction for normal forces means on the right edge, it's pointing towards right. On the left edge, it's pointing towards left. For V, it means on the right edge, it's pointing downwards. On the left edge, it's pointing upwards. And for the M moment, it means on the right edge, it's counterclockwise. On the left edge, it's clockwise. So having said that, now we can draw the free body diagram for this system. In order to draw the free body diagram, the first thing we always do is to replace the distributed forces by a single force, by a single equivalent force. And you can see here the length is 9 meters. It's a triangle. And the maximum of the force density is 270 Newton per meter. That means the area of the triangle is 270 times 9 times 1 over 2. And that would be 1215 Newton. So that's the value. Where does it act on? So what is the location of that? That would be basically the centroid of that triangle. So we know that if it is 9 meters, the distance from left for that centroid would be 3 meters from left and 2 meters from right, or if you want to think about it, it's 1/3 times the height from left, and 2/3 of their height from the right, from the peak. Okay, so that's that. Now the system reduces to this one, and then again we need to calculate first the reactions of the support that we have here. For the support reaction, we use the same convention. So basically it looks like you are cutting the member, but you are cutting it at point A. So if I cut it at point A, then this edge would be the left edge. So it would look like the left edge of the little piece that I have here. So basically I draw the forces in accordance with that. So I draw the shear force at A upwards, the normal force pointing towards left, and bending moment in a clockwise direction. And this would be our usual coordinate system. So once you have this system, everything is set. Now you can easily basically proceed. You have the free body diagram, you have all the moments acting on it, all the forces and moments acting on it, and then you have three governing equations: balance of forces in the x direction, in the y direction, and balance of moments with respect to any point. In this case, let's say balance of forces with respect to point A. So you should read this M with respect to point A. Okay, this is not exactly the same as we say here. So here, when I'm writing MA, this is actually the moment at A, but obviously here I mean moment with respect to A. But this shouldn't cause a confusion. Although we write both of them as just MA, I think it should be clear if we mean the value of moment or internal moment at A, or we just mean moments with respect to point A. So if you do that now in the x direction, we have only one force, and assuming that this is the plus direction for the x, that force comes with a minus sign, so you get minus NA equals 0. For the vertical direction, assuming that we have upwards as a plus direction, then you get VA in the upward direction and 1250 Newton downwards. So that would be your balance equation in the y direction. Obviously, if you chose a different directions for the xy coordinates, you would eventually get the same values for v and n. So it doesn't matter really how you choose your coordinate system as long as you are consistent. And then for the moments, for the balance of moments with respect to A, so with respect to A, you have the equivalent force 1215 at distance 3 meters, and it wants to cause a clockwise direction, a clockwise moment. And usually we assume that the moment direction, the plus direction, is counterclockwise. So for that matter, it comes with a minus. But also the moment that we draw at A, so the moment at A, the internal moment at A, is also clockwise itself, so it also comes with a minus. Again, remember, right now, when we are looking at this convention and when we are writing this equation, we just treat them as we usually did the external forces. Okay, you just treat them as usual, and you assume these are just external forces. You don't have to think whether it's internal or external. You need to only think about its direction being internal or external when you want to draw it. But once you draw it according to the convention that we have, then you just write the balance of forces and moments. Okay, so you have three equations, three unknowns. You can calculate all these values. Basically, you get Na0, Va 1215 Newton, and Ma now appears with a minus here, minus 3645 Newton meter. That means the direction that we chose is wrong, so it would have been in the opposite direction. So it would have been indeed counterclockwise. So you could, for instance, write it like this and then clearly show that it would have been counterclockwise, or mention that it is counterclockwise. Either way it works. I mean, as long as we use our convention and you have a minus here, that's perfectly correct and fine. But if you want to choose any different convention, in any case you should just get the same number and the same direction, regardless of the convention that you use. Okay, so we have that. Now we want to calculate the internal forces and moment at C. What we need to do is to cut this structure between A and C. So if we cut the structure between A and C, we would have this little part. Okay, and then this would be your external forces, your external distributed forces, and then you have also the reactions from A. But also you would have your internal loadings at C itself. So if you put them all together, this would be the new free body diagram. And then again, you can see kind of for this free body diagram, I have already chosen the values that we had from the previous part. So we know that MA is just 3645 and it's counterclockwise. I already put it like that. And then we know VA is 1215 upwards. So we have this. And then on C, it's on the right edge of the cutout. So the plus direction for VC would be downwards. For NC, again, it's in the extension direction, so it would be towards right. And for MC would be counterclockwise. So all you have to do is to now treat this free body diagram as you would usually do any free body diagram. And the first thing you want to do is to calculate the equivalent force for the distributed forces that you have here. So again, if I just clean up the additional parts, this is free body diagram that we want to proceed with. If I enlarge that piece, you can see that you have this 270 Newton per meter on the left, but then the slope of the line is 270 divided by 9. So it's 30 basically. And that tells you that at distance 6, so here, again, remember this is 0 here, that means it would be 180 here and 270 here, okay? Because the slope is 30. So per 6 meter, you get 180, and per 9 meter, you get 270. Okay, so now that we know this is the state of the distributed load, all you have to do is to split this into figures that you can easily calculate. And in this case, you can see there is a very nice rectangle at the bottom and there is a triangle on top, and then you can handle them separately and add the resultant parts together. If you think about the rectangular part, the distance is 3. The distance is 3. The height is 180. So the area of that rectangle is 180 times 3, that is 540 Newton. And it acts in the middle. Okay, so it's location would be in the middle of the 3 meter. That would be 1.5 meter. If you do the same thing for the triangle, the area of the triangle would be the height here, which is 90, the base is 3, and then you have factor 1/2, so you get 135 Newton for the triangle. And then again, the distance would be height divided by 3 from the base. In this case, it would be 1 meter. So if you put all this together, essentially this is what you have. This would be the 540 is the resultant force from the rectangle. 135 is the resultant force from the triangle, and they act at the distances 1 meter and 1.5 meter respectively. And then you have the forces at A. You have these 3 unknowns at C. All you have to do is again to treat this as a common free body diagram and treat this with our usual governing equations. So our usual governing equations in 2D are balance of forces in the x direction, in the y direction, and balance of forces with respect to a point, let's say A. If you do that now for the balance of forces in the x direction, you can see you have only NC. So NC would be 0. For the balance of forces in the y direction, you have 540 downwards, 135 downwards. So they both come with a minus. You have 1215 upwards, and then you have VC downwards. So you get VC to be 540, and balance of moments with respect to A, you would have the moment due to force 135, and then you can see that it wants to turn this in the clockwise direction. So you get distance times force with a minus sign. The force 540, it wants to also turn this clockwise. The distance is 1.5. So you get minus 540 times 1.5. Then you have the moment at A itself, which is 3645, and it comes with a plus sign because it's counterclockwise. And we have assumed that counterclockwise is plus. Now you have the moment with respect to VC. The moment with respect to you have the moment of VC with respect to point A. That would be the distance 3 times VC. And then again, it wants to cause a clockwise rotation, so it would come with a minus. So minus VC times 3 plus VC plus MC, the moment at C. And if you do this, and since you know that VC is 540, you insert that here, you get MC to be minus 1080, telling you that the direction you have chosen was wrong, so it would have been basically in the opposite direction. But that's it, essentially. You wanted to calculate the internal loadings at cross-section C. Now you have it. The normal force is 0. Shear force is 540. Moment is minus 1080. Or you can say moment at C, well, according to this convention, then you know it's plus 1080 in the clockwise direction. Exercise 2 of this lecture is similar to problem 1.3 on page 13 of the Hibbeler book. You are asked to determine the resultant internal loadings acting on the cross-section at G of the beam shown in the figure, and also you are told that each joint is pin connected. So point G is here. That means you want to know what is the state of the material at this cross section. So if you cut the material at G, what is N, what is V, and what is M? Also, you are told that each joint is pin connected. That means the joints here, they cannot carry any moment. They only carry forces. So these are similar to joints that we have in truss structures. Okay, and then you have a distributed load from 0 starting at E, going all the way to 600 Newton meter at D. You have also a force of 1500 Newton downwards at A, and the distances are also shown here. In order to calculate the state of the material, again the forces and moments, we need to know what is the force at AB. And we don't know that. So basically that's how we are going to approach this problem. We will solve the problem as we usually do, but we know that we want to come here, and we know that we don't know the forces in member BD and BA, and they are necessary to calculate the forces and moments at G. So it's basically a two-step process. First, we need to calculate these, and then we can come to calculate these. But also it's more interesting than that, because in order to calculate these two, we need to calculate the reactions at the supports, like truss structures. So that's what we do. We start with the free body diagram of the entire system. If you draw that, then at point E and C, you would get reactions in both x and y directions. They are both fixed, or they are hinged. So you get two forces. None of them is a roller. So each of them would give you two unknowns. Then you replace the 600 Newton with one equivalent force. So it's 600 times 3 times 1 over 2. So the force would be 900. And the distance of the force from D would be 1 meter. Again, one third of the height, or 2 meter from E, as it's shown here. Okay, so this is the free body diagram. Now, from this free body diagram, we need to calculate the support reactions. However, as you can see, there is a little problem here, because we have a two-dimensional problem. We have three equations. We have our usual governing equations, and that's all we have, and that's three equations. And we have four unknowns. So what do we do? If you look at this member, you can see that it's a two-force member. So it has only a force acting on its left corner or left end and on its right end. Okay, so because you have only two forces acting on the left and on the right ends, that means it's just a two-force member. And if you remember, we said if you have a two-force body or two-force member, the forces acting must be of equal magnitude in opposite direction and along the same line of action. So basically that tells us that Cy cannot exist. Okay, so the only force that you can have along the member would be Cx. That's it. That's a huge relief, because now you know only you have three unknowns and you can solve them with your three equations. The three equations, again, we do balance of forces in the x direction, balance of forces in the y direction, and balance of moments with respect to any point, in this case with respect to point E, and we also pay attention to the plus direction as we always did from the beginning of the course. So this is a very standard problem right now. All you have to do is to write these balance equations. In the x direction you get cx and ex, so the sum of cx and ex is 0. In the y direction you have ey upwards, you have 900 downwards, and you have 1500 downwards, so they come with a minus sign. And then with respect to point E, if you want to write the moments, you can see that assuming that counterclockwise the plus direction as we did, you can see that the force 900 would be multiplied by 2-meter arm, and it wants to cause a moment in counterclockwise direction, so that comes with a plus sign. Then you have the force 1500 with the distance 5 meter that also causes the moment in the counterclockwise direction, so also comes with a plus sign. So 1500 times 5 meter. And then the force Cx, it has the distance of 1.5. So the distance between C and E is 1.5. And it wants to cause a rotation in the clockwise direction, so it comes with a minus sign. So basically you get these three equations, and from three equations you can calculate the three unknowns. Cx would be 6200, Ey would be 2400, and Ex would be minus 6200. And that makes sense because you can imagine these two forces are the only forces in the horizontal direction. They need to cancel each other, so one of them is just the opposite of the other one. Okay, so until now we have the reactions from the supports like we usually did for truss structures. The next thing we want to do is to move forward and calculate the force in AB. In order to do that, we need to split the structure. So if you think about it, you can cut this at member BC, or basically you can imagine that similar to what we did in method of joints, you can imagine that since we know Cx is 6200, FBC would be 6200, and that would be a tension. So it comes with a plus sign. I mean, from the direction you can clearly see this is a plus direction, it's a tension. So what you want to do next is basically to write the equilibrium of forces on joint B. So on joint B, now you know FBC is 6200. You don't know what is FBA, you don't know what is FBD. So you don't know this, you don't know this, you know this one. But then you basically have two unknowns and you have two equations. So from two unknown two equations, you can solve them. And if you do that, I don't do it because it's very simple and it's exactly what we did in method of joints. If you do that, then FBA would be 7,750 Newton, and FBD is minus 1,400, minus 4,650. That means it's not downwards, the direction that we assumed. And then again, the directions that we assumed, if you remember, it's always pointing away from the joints, showing that it's a tension direction. In this case, it means the member BD is under compression. Okay, so it would have a minus. All right, we are almost there because now you know exactly what is the force in member AB. And once you have that, now you can cut the structure like this, and we can basically tackle the main part of the problem, which was to find the internal loadings at G. Now, if you do that, if you cut the structure like this, you know that at A, you have just 1500 Newton downwards. You have FAB, again, in the tension direction, so that's 7,750 Newton. And then for G, you should remember our convention. So if you cut it like this, G is the right end. So the convention would be to have the shear force downwards, the normal force pointing towards right, and then the moment to be counterclockwise, to be positive. So we draw them, and now you have a much simpler problem to solve. It's again a very, very common problem. It's exactly like a free body diagram, and all you have to do is to write your balance equation for this free body diagram. Also, you remember that this angle alpha, it follows the famous triangle. So we know the distance here is, well, the distance here is 2. The distance here is 1.5. So basically the distance AB would be 2.5. So it has the 3, 4, 5 triangle. So we know what alpha is. It's not an unknown. Anyway, this is the free body diagram. And then you can write your governing equations again, balance of forces in the x direction, in the y direction, and balance of moments. And then again, at this point, you just treat this as usual, as if these are all external forces. You don't have to be concerned about anything. In the x direction, you would have ng plus the horizontal component of the force, so 7,750 times cosine alpha, the sum of those would be 0. In the y direction, you have 1,500 downwards, Vg downwards, so they appear with a minus. And then you have the vertical components of the force in AB in the upward direction, so that would be 7,750 times sinus alpha upward, so it comes with a plus sign. And then the moments with respect to point A, you have basically the moment of G, which is counterclockwise, so it is with a minus sign. And then you have the moment due to shear force Vg, that would be Vg times the distance, and the distance is 1, and it tries to cause a rotation in clockwise direction, so it comes with a minus. So essentially you have 3 equations, 3 unknowns. You can calculate them. You get Ng minus 6,200 Newton, Vg 3,150 Newton, and Mg also 3,150, but Newton meter. So pay attention that one of them is force, one of them is moment. That's it. So you were asked to calculate the internal loadings at cross-section G, and these are exactly what you wanted to calculate, and there you have it. So remember what was our initial goal of this lecture. We wanted to talk about stresses, and we said that in order to talk about stresses, we need to talk about these other quantities that go hand in hand with stresses, and they were internal forces and moments. So at this point, we know the internal forces and moments. Basically, we know what they are, we know how to handle them, we had 2 exercises on them, and based on that, we can come to stresses, and we can explain what stresses are. Remember the body cut out that we had previously. So we said if we have a body and we cut it somewhere in the middle of this body, let's say if you have a cross section, you would have a lot of forces acting on that cross sections, and these are internal forces. Okay, so we are talking about the internal state of the material. Now you can imagine each of those little forces, it's acting on a little incremental area. And if you assume this is your coordinate system xyz, you can assume that your area in this particular example is exactly aligned with the xy plane. So that little incremental area is also on the xy plane. So if you think about your force delta F, it has three components. It has a component in the y direction, in the x direction, and in the z direction. What we want to do is to normalize this force by area. And basically, we want to define this quantity that is force per area. And it turns out that defining this normalized quantity helps us to better understand and explain the material behavior. Okay, so essentially, there is a useful quantity, force per area, and you can imagine its unit is Newton per meter squared or Pascal. And we call that stress. So stress is nothing but force per area in principle. And then again, it's conceptually speaking. We will talk about different types of stresses, and later we will see why it's useful for material behavior to use quantities such as stress. But for now, just imagine conceptually it's like force per area. And then again, if you remember what we just did before, we said when you talk about resultant internal forces, you can think of normal forces, N, and you can think about shear forces, V, on any cross section. So any force that you think of, it has a component on the tangent plane. In this case, this would be the shear force, and this would be the normal force. Okay, so it would have a component that lies on the plane, and that's a shear force, and then it has a component that is normal to the plane, and that's a normal force. So having two different types of forces means that you can also have two different types of stresses. And basically, the stress that is caused by normal force is called normal stress. The stress that is caused by shear force is called shear stress. The normal stress is shown by letter sigma, and shear stress is shown by letter tau. So basically, if I want to now write them mathematically, you know that sigma z, and then z stands for the direction. We know we are talking about this area whose normal axis or normal vector is k, or is the z-axis. So we can call that sigma z. So the normal stress in the z direction would be that delta F, the little force, divided by that little area, but the component, the z component of that force. So let's call this delta Fz. Okay, so if you think of that delta Fz to be the component of that delta F in the z direction, you divide it by that area and then assume that that area goes to 0. Okay, so this is a limit process basically, meaning that you want to define this locally. You don't want to define it in a sense of a average quantity. You want to define it at a point. So for that matter, we want to consider that limit. Okay, so that's the normal stress. But now when you want to talk about the shear stress would be this component of the force. So the component of the force in the xy plane. So imagine that this is the vertical component. So if now you think about this component and you divide it by area, you get the shear force. But already you can see that that component on the plane itself, it has two components. Okay, so when you talk about shear stress, you can also talk about two components of the shear stress. So one of them is in the y direction, one of them is in the x direction. So basically, you can talk about tau with two information. One is the first index, z. It shows you, similar to the z that we had here, it shows you the normal vector to the plane at which you are calculating the stress. The second component, the second index, it shows you the direction. Okay, so basically if you want to do that, you want to divide delta F in the x direction by delta A. And if you want, you can imagine this is like delta A in the z direction, because the normal vector to that delta A is k. Okay, it's the unit vector in the z direction. So that's that. And then again, you can do the same thing for tau zy. So you have, again, an information. The first index tells you on which plane you are, and the second index tells you in which direction you are. So in this case, you would divide delta Fy by delta A. Again, you can imagine delta A has a component Z. In this case, it doesn't matter if you write this Z, but we will come to that later. So if I want to kind of summarize this, this is exactly how it works. You think of that normal plane. The normal plane has a unit vector orthogonal to that. Okay, so that little incremental area, it has its own normal vector, and the normal vector, in this case, the surface normal vector is k. And for that matter, we are having these z indices here. Okay, so the first index in a way. And as I said, when you want to define this, you can write delta A also by an index to make it more clear. But then you also talk about the components of the force. Now, if the components of the force is x or y, then you use that component as the second index. If you talk about the normal stress, it makes no sense to write the same component again, because you know it's a normal stress. So you can imagine sigma z is something like equivalent to sigma zz. Okay, so we know we are talking about the normal stress, so we know these two would be the same. It doesn't matter if you say I'm showing the first or the second index, they are the same index. Okay, so again, to make it very clear, it's exactly how we do it in the sense of normal stress. The fact that we show it by the letter sigma, one index would clarify the direction and the plane. If you talk about shear stress, then you need two indices. The first index would clarify the plane, so that would show you the surface normal. The second index would show you the direction of the force. And then again, it's exactly shown here. So if you have a letter sigma, you would have only one index, and that index is the normal force component as well as the surface normal. If you talk about the shear stress, you have two components. The first one is surface normal, the second one is shear force component. Okay, so you should kind of get used to it. This is also a sort of convention of showing it like that. You can imagine of different ways of showing the same information, but this is how we do it in this lecture and in this book. So now we want to extend the same idea, and let's say, remember this body itself, it was, let's say you had like an egg kind of, and then you cut that in the center. Now imagine you make another cut. and you come to this. So if you do that, you can see basically you would have two surfaces that are on those two separate corners basically. And then for each of them, you can play the same game that we just learned here. But interestingly enough, you can see that the surface normal on the upper surface is k, so it's like a z-axis. But on this plane, the surface normal would be j vector, so it's like a y-axis. So if you think of the components of the shear stress on this surface, their first index should be y, because the surface normal is j vector. And on this plane, the first component is z, the first index is z, because the surface normal is k, is in the direction of the z-axis. Now the second component though, you can see these two vectors or these two shear stress components, they point in the same direction on two different planes. They both point in the direction of the x-axis. So this is our coordinate system basically. They both point in the x direction, so their second component is x. But you can see their first component is different, or the first index. Okay? So they are in the same direction on two different surfaces. The same thing holds, or a similar thing holds here. You now talk about a shear stress that is on the plane normal to j, so the first component is y, but then in the z direction, so now you get z. But here, then you talk about a shear component that the first component, the shear stress, that its first component is z and its second component is y. And you can kind of see that these two, although it looks like you exchanged the two indices, they are very different quantities. So the order matters. The order matters and is very important. Okay, so what I want to do next is to play the same game. So basically, again, remember, this thing was a kind of an egg-shaped body, and we cut it once, and then we cut it twice. So I want to cut it again. And before doing that, by the way, I tell you that these two normal stresses, you can also show it here, but in order to avoid confusion, I didn't show it in the previous picture. Okay, so now if you cut it again, you can see that you actually have a cube, and this cube has three surfaces, and then each of these surfaces has its own surface normal according to our usual coordinate system. So basically on each surface you can play the same game and you can show the components. So I'm trying to do that, and then I am basically drawing this larger figure to talk about that. So we want to talk about the general state of stress at a point. And then again, remember, we have normal stresses, and for normal stresses, we have only one index, one subscript, and that shows the normal axis to plane. For shear stress, we have two indices. The first index shows the normal axis to plane, similar to before. The second index shows the shear force direction. So it shows the direction. Now, if you think of that cube that we had just in the previous picture. So basically it could be just a cut cube from inside the material. If you think of that cube and we look at the top surface, on the top surface, the normal axis to plane would be z. Okay, so the unit vector would have been k, basically. The unit normal vector to this plane would have been vector k. So based on that, we know if you want to write the stress state on that surface, you would have sigma z, and then you have two components of shear stress. For both of them, the first index is z. So you have tau zx and tau zy now. Now tau zx points in the x direction, tau zy points in the y direction. So these are the three stresses on that upper surface. On the side surface, the normal axis is y. So again, if you think of the unit vector normal to this would be your usual vector j. And based on that, the normal stress would be sigma y. The shear stresses would be tau y x, tau y z. Now, tau y x points in the x direction, tau y z points in the z direction. Finally, we can draw this for the front surface. For the front surface, the normal vector would be I. So the normal axis to plane is then axis x-axis basically. So your normal stress would be simply sigma x. And your shear stresses are tau xy and tau xz. And then again, tau xy points in the y direction, tau xz points in the z direction. So you get, let's say, 9 components based on these three surfaces. You can imagine that there are 3 other sides to this cube, and you could have played the same game on those, but everything that happens on these sides, it kind of reflects on the other sides in a sense of an action-reaction type. Okay, so I'm not writing it, but we will talk about it in the following slide, and you will see that essentially the stress state would have 9 components. So these 9 components are enough to show the stress state at a point. But also more importantly, you will learn that 6 of them would be enough. So it's not even 9, it's actually 6, and we will talk about that soon. But for now, just remember this, that when we talk about the state of stress at a point, it is not a number, it's not a scalar value, but it's also not a vector. I mean, forces are vector, but now we are talking about this thing that, precisely speaking, it's a tensor. Okay, so it's not a vector, it's not a scalar, it's like a more complex concept than just a vector, and we call this a tensor. For you, you can just imagine it's a matrix. Okay, and then again, this matrix, stress matrix, is equivalent to the graphical representation that we had here. Okay, so when you talk about a stress state at a point, you can either show that stress state using a matrix or using a graphical representation. You must keep that in mind. You must have this picture in mind, and you must very well understand the structure of this stress matrix. You can see that on the main diagonal components, you have sigma x, y, and z, and then you have tau xy, tau xz, tau yx, tau yz, tau zx, tau zy, and sigma z here eventually. So there is kind of a usual counting on it. So you can think of, I don't know, maybe you want to think of it as one component. So this would be like 1 2 component, and if 1 is x and 2 is y, then this would be like 2 1 component, and then 2 1 component would be yx essentially. So it has that kind of a structure. It doesn't matter how you want to remember it, but as long as you remember it, I think you would be able to solve the problems that come with this. To better understand this, we are going to have a few examples together, and we show how you can find the stress state from a graphical representation. All right, so we want to show some examples of stress states in the material and see how we can write them in matrix representation. And then again, remember, this is the matrix representation that we talk about. Here is the first example. If you think of this example, now you can see that on the upper surface, you have a shear stress tree pointing in the y direction. So that would be something like tau zy. If you think of this one, this is on the y surface and it points in the z direction. So that would be tau yz. Then this 4 here is like sigma z, and 5 is sigma y. So basically you have these 4 components, and based on what we had here, you know now which of them are which. And this would be the matrix representation. This is your stress. And you can see that on the front surface is the surface with x-axis to be the normal vector. So basically the components on that are sigma x, tau xy, and tau xz. And all of them are 0 because you have nothing there. So that's the first example. Then you can think about this. Now thinking about this, you can see that on the front surface, on the x surface, that would be your first row. And then again, remember here, this is like sigma x, tau xy, and tau xz. So sigma x is 0, tau xy is 0. You have only tau xz. So there is only something on that surface pointing in the z direction, but in the opposite direction of the z-axis, basically. So it comes with a minus. So that would be 0, 0, minus 6. And then you would have minus 5 on the y-plane. On the y-plane, you can see that you just have one normal stress. So that would be your sigma y. And sigma y is minus 5. Again, it's like a compression, or it's the opposite direction of the y-axis. On the upper surface, on the z surface, you have no component in the y direction. You have no component in the z direction, so normal. You have only this one in the x direction, but then again in the opposite of the x direction, and that is then also minus 6. Okay, so you get minus 6, 0, 0. That's example 2. In the next example, we can see this one. In this one, you can see there is nothing on the normal stresses. So all the 3 normal stresses are 0. So basically the main diagonal components are 0, and then you are left only with shear stress component. Now for the shear stress components, we start from the x plane. On the x plane, and that would be the first row, you would have 3 in the y direction and you have 4 in the z direction. On the y plane, you have 3 in the x direction and you have 2 in the z direction. On the z plane, you have 4 in the x direction and 2 in the y direction. So you also get that. Now finally, let's look into another interesting example. This would be an example kind of opposite to this. So in this one, you had no normal stress and it was only shear stress. Now here you have no shear stress. You have only normal stress. And in this case, in particular, all the normal stresses are pushing. So all of them are appearing with a minus sign. This would be a particular example of hydrostatic pressure. So if you think about it, usually in fluid mechanics for inviscid Newtonian fluids, you assume that shear stress is 0. And then you only talk about pressures in fluids and in liquids. This would be exactly what you would do in fluid mechanics. And then let's say if this was a fluid mechanics example, you would say the pressure is 2 and 2 Pascal. So this is how the concept of pressure in fluid mechanics actually connects to the concept of stress in solid mechanics. The next thing we want to talk about is the concept of average stress, and then a little more about the components of the stress itself. But before I do that, I want you to just pay attention to one interesting fact about all these examples. Every matrix here has a very interesting property, and they are all symmetric. Now, having them symmetric here was just for convenience. So these are examples. They didn't have to be symmetric. But we will see that the symmetry of stress is actually a physical property of stress. Okay, so this assumption that we just assume they are symmetric here, this is actually a correct way of defining stress, or it's the correct way that stress forms inside the material. We will talk about that next. So the next thing we want to talk about is shear stress equilibrium. And if you think of the same graphical representation of stress state that we had, we basically want to think of what happens to shear stress on this plane and on the plane opposite to that. So these are the planes essentially along the y direction. And also we want to focus on the components in the z direction. Okay, and then basically having those two surfaces in mind, now we also talk about the upper surface and the bottom surface, where we consider the other shear stresses with similar indices. So you have tau yz. So here I want to talk about tau zy. And then obviously what happens at the bottom. So what I'm going to show you is more like an example to do the shear stress equilibrium. But it can always be done on different surfaces, and you can play this game. And basically what I'm saying is general enough in the sense that we develop it is general, but we just do it as an example for these particular surfaces and directions for now. So here on this surface, I know the shear stress would be tau yz. On top, the shear stress would be tau zy, and then again, maybe you should remember this is more like this. So we are still talking about a three-dimensional problem, but I'm talking about a cut for simplicity. On the left area, I use the same indices, so tau yz, but I'm using tau prime. Okay, so it may be a different value. I'm not assuming that they are equal. I'm just using the same indices to show the direction according to our direction criteria. And the same thing holds here. So I have a prime here, and I'm not assuming that they are equal, but it shows the direction according to our convention. It's fine. Now, if you think about these two, so let's say on the right and on the left hand side, if you think about these two sides, and assuming that this cube has, for instance, dimensions delta x, delta y, and delta z. If you assume this cube has these dimensions, then you multiply this shear force or shear stress, you multiply the shear stress by the area and you get shear force. So the area here would be delta x, delta z, because this is delta x, this is delta z. So the area is delta x, delta z. You multiply it by shear stress, you get the shear force, and this is the upward shear force. You do the same thing on the opposite side. So you multiply shear stress by the area, you get the shear force on the other side. But then you also know that the sum of forces in the z direction must be 0. So basically this tells you that these two must be equal. So delta f and delta f prime must be equal. And because they have the same area, this tells you that essentially these two are equal. So the shear stress on the right and left are equal. These particular components. And then again, you can play the same game with different components and come up with a similar result. Now, if you play that exactly with the components on top and the bottom, you come up with the same answer and you have the same conclusion. But then in order to do that, you would be looking at the sum of forces in the y direction. Okay, so maybe you can kind of see where I'm going with this. We usually talk about equilibrium equations. Now, this is equilibrium in the z direction, equilibrium of forces in the y direction. You can now think of equilibrium of moments, for instance, with respect to x-axis. So if you think about writing equilibrium with respect to x-axis, and that axis would be here essentially. Okay, so maybe you look into this point. Remember, this is like a front view of what we have. So we are talking about the equilibrium with respect to this point or with respect to this axis. If you do that, then these two do not impose any moment, but then we would have the moments with respect to these two. Now for them, tau yz would be multiplied by this area to give you the shear force, and then the distance would be delta y. So you get that moment, and that would be the counterclockwise moment. But then tau zy would have the distance delta z, and it will cause a moment in the clockwise direction, and the area would be delta y delta x. But they should be equal, and you can see now these two are essentially the volume of the cube, and they are equal. So they cancel with each other, and then eventually you see that tau zy and tau yz are equal. Okay, so basically you should remember that at the beginning we didn't assume that the left and right shear stresses are equal, but now we know because we had the balance of forces in the z direction. Then we didn't assume these two were equal. So at the beginning we had a prime here, if you remember. But I'm not writing that prime anymore because at this point we know They are equal. We just proved it. And then you have balance of moments, and we also proved that these are equal. So this is a very interesting property, because as soon as I tell you tau yz is something, so if you know tau yz is 5, you also know tau zy is 5. Okay? And essentially, coming back to what we did, if we want to summarize it, we just used 3 equations, 3 unknowns, and we solved this problem. But what it means in summary is that stress is symmetric. And this is what I just told you or showed you in the previous examples. Okay, so you always assume tau xy and tau yx are equal, tau xz and tau zx are equal, and tau yz and tau zy are equal. And then again, this is not an assumption. This is essentially the consequence of the balance of moments. Okay, so that is the way the stress develops in the body to retain its symmetry. Okay, so stress is symmetric. We know that. One last topic for today. We want to just introduce average stresses. It's a fairly simple topic. So basically, usually we talk about stresses at points, and they are local values at points. But you can also think of average stresses. So you can think if you have a bar and then you apply a force, obviously stress at different points could be different, but you can always think of an average sense of it. So you can just, instead of writing it always as df with respect to dA, you can just kind of think of it as the average of the total force by the total area. And usually working with these average stresses is a good point to start with your design, and that's why we define it. So for the normal stresses, it's just the total force divided by area. For the shear stress, we also define this thing called average shear stress. So average shear stress is, again, the total shear force divided by total area. And if you think of an example like this, let's say you have a slab here on top of 2 bases, and you apply a force F on top of it. Basically what you get would be 2 shear forces on the 2 sides to keep this in equilibrium. And those 2 shear forces together, they would result in shear stresses. We can try to find what is exactly the distribution of those shear stresses on each side. But for now, we don't want to do that. We just want to say, well, we know the area here is A. So if you know the area is A and the shear force is V, then tau average would be VA. And by the way, in this example, you can imagine that 2V would be F. Okay, so it has 2 sides. So from the force, you can calculate V, and from the V, you can calculate the average shear stress. So that's it. That's basically the concept of average stress. And as I said, it's usually a good point to start your design, and that's why we learned it now. So this was our first lecture on the concept of stress. We have 2 lectures about stress, and today we covered sections 1.1 to 1.5 of the first chapter of the 9th edition of the Hibbeler book. We have 2 more exercises on this, and we will do it at the beginning of the next lecture, and then we continue our discussion on stress. Catch you in the next one.